Berkeley, Netherlands, and again in Germany. He came back to the States at the chemistry department at Michigan State University. She's a very well-known scientist in the area of molecular magnetism, especially with rare earth. And she gave a lot of talks in more than 60 countries, but she is the first time that is delivering a talk here in Turkey, which is a special country for her because his parents, family are coming from here. And then the title of the talk is Large Coercitivity and Magnetic Blocking in Lanthanide Single Molecule Magnets. You have 40 minutes, and I will tell you when the time will be over. No, later.
For the introduction and invitation. I'd like to express my gratitude to Selvan Demir for the invitation and all the organizers for a nice conference so far. Let's hope this works because I'm doing this now differently. Do you hear me?
I don't know. Sorry, I don't know if we are broadcasting this by Zoom platform.
Is this working? Yes. Okay. All right. So as Javier just said, I am going to talk about lanthanide-based single molecule magnetism today. So shown here is a size scale that passes through 3 overlapping regions of magnetic materials. At the left, we have 3-dimensional permanent magnets whose physics is defined by the interaction of magnetic domains containing very large collections of spins. If we start to shrink down the size of these particles, they will reach a point where the particle becomes single domain, which is the so-called superparamagnetic limit, and that actually represents an interesting problem for storage media. If instead of shrinking down further, which becomes difficult because of size and aggregation control, the smallest size regime is explored by a bottom-up approach, meaning we use coordination chemistry to design discrete molecular species and study their magnetic properties. And the magnetism of these molecular species is then defined by the individual magnetic moment of the molecule, which usually displays a number of quantum effects not observed elsewhere, such as discrete quantization of the spin orientation or quantum tunneling of the magnetization. So permanent magnets have entered our daily lives in many ways, and I know for this audience I don't have to explain this in detail, but here are shown 2 examples. For instance, here in the motors of wind turbines or the motors of hybrid cars where magnets are used. And usually these motors are lighter, more robust, and have a longer lifetime than their unbrushed counterparts. But the potential applications of single molecule magnets are even more remarkable. Magnetic thin film coating of hard disks could allow high density information storage as high as 31,000 gigabits per square centimeters, which would be a huge amount of data storage capability. Other areas of application include quantum computing and magnetic refrigeration. For instance, shown here is a chip that has been developed by NASA. It's designed to operate as a 128 qubit quantum processor. Okay, so the entire field of single molecule magnetism started off, it's not working? Started off some 30 years ago. This pointer is not working. Okay. Which is, was established about 30 years ago, namely with the discovery of this first single molecule magnet, which has been this manganese cluster complex, subject of countless physical and chemical studies. Although its structure seems a bit complicated, its basic magnetism can be rationalized fairly easily. So the central tetrahedron of manganese 4 ions here each contribute 3 halves to the total spin and are coupled together ferromagnetically. These in turn are coupled antiferromagnetically to the outer manganese ring, leading to a net spin of 10 within the molecule. And because of an exchange coupling within the cluster, the molecule can indeed be modeled as a single spin orientation of S equals 10. However, molecular symmetry and single ion effects lead to not every orientation of this giant spin having an equivalent energy, which leads us then to a description of the magnetism of single molecule magnets as double well potentials, where by stable orientations of the ground, this is not working again. Okay, so we can describe this as with the double well potentials, whereby stable orientations of the ground state are separated by a barrier to spin inversion. So going from spin up here to spin down here requires the moment to climb and descend this energy barrier, which is a function of the ground state spin S and the axial anisotropy D. What was truly remarkable, though, was that this molecule actually showed magnetic hysteresis, just like a bulk magnetic material. Magnetic hysteresis measurement is a variable field measurement, and for us the ultimate test for magnet-like behavior because it relates to the magnetization properties of a material by which it firstly becomes magnetized and then demagnetized. So after reaching full magnetic saturation, meaning all spins are aligned along the external magnetic field and sweeping the field back to zero, we're basically interested in two values of what every magnetic hysteresis loop should exhibit. The one value is called remnants or remnant magnetization. That's the magnetization left behind after removing the external magnetic field. The other value is called coercivity or coercive field. That's a reverse field required to drive the magnetization back to zero after having reached a full magnetic saturation. And so if we think about the idea of really implementing single molecule magnets in technology, we really would like to have these values as large as possible, and we would like to observe these nice magnetic features at substantially higher temperatures than this first single molecule magnet. Okay, so how do we do this? There are now a lot of different strategies, and I can tell you that the current most successful one are two. But the initial one was very important in the development of the current strategies. So perhaps somewhat intuitive idea was to just increase the number of spins, right? Let's just add more metal ions. If we do this, then we can generate like huge cluster system, manganese clusters of up to like 84 atoms. And there are like a lot of manganese clusters in between them. This is just like one summary slide basically. But the crucial result from all these studies from many, many research groups was the larger you go with the spin number, the smaller D gets. D is the magnetic anisotropy. So you're losing magnetic anisotropy by doing this for transition metals. And that is because of the complicated interrelationship between these two parameters, S and D. Okay, so then this was about 10 years of research. Then researchers thought, okay, let's deal with this second parameter. Let's try to get this larger, D. How do we get the magnetic anisotropy larger? And one viable way is to just move away from transition metals, namely to lanthanides, which due to very large unquenched orbital momentum and strong spin-orbit coupling have huge single ion anisotropies. In fact, really unique in the periodic table. This is the lanthanide series, and I'm going to focus on two of the trivalent lanthanide ions, namely terbium and dysprosium, because both of them are highly magnetically anisotropic. The energy gap between the ground and the first excited state is often large. The most significant difference between both ions is that dysprosium is a Kramer-Zine, meaning it has an odd number of electron counts. As a consequence, ground state is always bistable, irrespective of the ligand field symmetry. And that explains why there's so many more dysprosium-based single molecule magnets known than with any other lanthanide. However, trivalent terbium is a very important ion, although it's a non-Kramer-Zine, because its ground state can be bistable if it's either placed in a rigorously axially symmetric ligand field environment or if it's employed in a strong exchange bias. If either one is being implemented, then actually trivalent terbium leads to very good single molecule magnets. And historically, the first records in the field were really done with trivalent terbium in terms of highest hysteresis temperature or highest spin reversal barrier. Okay, to give you some examples. For instance, trivalent terbium gives very high spin reversal barriers in such lanthanides, phthalate complexes, which were, by the way, the first lanthanide-based single molecule magnets prepared at the time from the Ishikawa group. But also dysprosium can give rise to really high barriers, for instance, in such lanthanide alkoxide complexes, where the dysprosium ions are bridged to one another through dimagnetic bridges. Okay, and that type of interaction is referred to as super exchange. While this can be quite large for transition metals, for lanthanides it's typically very small. And that is due to a limited radial extension of the 4f orbitals. Now, if there's no coupling present, or if there's very weak coupling presence, molecules, although showing these high barriers, deviate from thermally activated behavior at such high temperature that there is only a very small remnant magnetization left in the hysteresis loop. So in other words, the hysteresis we observe in many of these cases, if we at all observe hysteresis, it looks like this. It's called butterfly hysteresis or waist-constricted hysteresis, meaning we can fully saturate the system and then we can sweep the field back and you lose all remnants. So if we really want to store information on that molecule, that would not be possible. And why is this happening? So instead of the spin is actually going over this preferred thermally activated barrier, it just tunnels through the barrier. This is due to an alternate relaxation process, which is called quantum tunneling of the magnetization. Okay, so this is a challenge, and one way to meet this challenge is to come up with a good strategy that circumvents this. And a really powerful method is introducing radical bridging ligands. These are open shell ligands with diffuse spin orbitals that can penetrate the core electron density of the lanthanide ions. If you do that, then you can indeed suppress this undesirable relaxation pathway through the quantum tunneling. Okay, so this is sort of the physics behind what I'm going to talk about now next, which is the chemistry approach to the physics problem. Okay, so we want to implement radical bridging ligands in between lanthanide ions. So this is one strategy. It's still a very good strategy, and it's one of the two most successful strategies still, but synthetically incredibly difficult, chemically incredibly difficult. And what I'm going to show you now is our approach, which is really has several factors. So first of all, we're exploring radical bridging ligands to see which one can really give strong coupling. And another important challenge here is that we saturate the metal centers chemically so that they don't have open metal sites, so you can prevent polymerization or in any case, you reach stabilization of the metals, okay? All right, then, so this is how it looks like. So we need a very viable precursor complexes. This is all organometallic chemistry, what you see here. And I'm going to talk about this molecule in particular. So this is a pentamethylcyclopentadienyl ligand. It's a carbon-based ligand. It's anionic, and two of them are coordinating to a trivalent lanthanide ion. And then you have a tetraphenyl borate anion, a very weakly interacting with the metal center. This is going to be very important because what this molecule can do is you can either, because it's only weakly coordinating, either you can insert a neutral ligand between this, or you can employ this in salt metathesis reaction. These are salt elimination reactions where you can precipitate the tetraphenyl borate out of the reaction. Okay, so this is a very great molecule to work with, but it requires several steps to make it. I'm not going to go now into great detail here, but you can make this, and then this is our first fragment, right, of what we want to achieve. We will have here the SpisCB star lanthanide scaffold, and I'm going to try to introduce now a radical bridging ligand in between this and a second of this fragment. Okay, that's the idea, and this is how it sort of started. We're able to take this and add it with a redox active bridging ligand like bipyrimidine, and then reduce it. It's a reducing agent, KC8, which then gives rise to this bipyrimidal radical bridged lanthanide complex. We have now indeed a spin on this ligand, and the lanthanides have their own spins. And you get very strong coupling by doing this. And once this is accomplished, then if theory holds, we should get to open magnetic hysteresis loops. And indeed, that was the case. So we were able to get to open magnetic hysteresis loop up to 7 Kelvin, so much better than the manganese cluster I just showed you. Okay, and then another system we worked on is another redox active bridging ligand, which is called Tetrapyridial Pyrazine. This is basically this here. This is the radical form, and a somewhat similar synthetic fashion was the reaction of two equivalents of this with one equivalent of the ligand and one equivalent reducing agent produce this bimetallic system. And again, we have a radical. And as you can imagine, for such a large ligand, the radical is going to be more diffuse, which potentially leads to weaker magnetic exchange. And indeed, this was the case. So we have a weaker than what I just showed in bipyridine, but remarkably strong, however. And because that's the case, the theory still holds. So we get open magnetic hysteresis loops up to 3.5 Kelvin in this case. What is really nice about this particular system was we could actually reduce this some more with two equivalents of Kc8 to another radical bridge system. So that has now 3 electrons, basically, 2 paired, 1 unpaired. So it's 3 minus, this is 1 minus. And the idea was here, by increasing the charge, that should actually increase the coupling between the lanthanides. And so we also did a lot of electrochemistry, and you can see here 4 redox events happening, suggesting 5 possible oxidation state for this ligand. And what we've learned from this system in particular is when you have this trianion as a bridge, then the magnetism changes quite significantly. And our explanation to why this is happening is was then based on DFT calculations, what we've done, and we could encounter a doublet ground state for the trianion, and then also a very different spin density distribution towards the lanthanide ions. So we learned from this project not only the coupling between the spins is important, but also orbital symmetry must be at play. Okay, and so that's how we're canvassing several ligands, and each of these compounds is highly reactive. Another system we're looking into is Bipedal Tetrazine. This is the first dinuclear tetrazine radical bridge lanthanide complex, and we can see strong coupling here, and also magnetic blocking. And synthetically, it's much more reactive, actually much more sensitive. So the radical is not stable in polar solvents like THF, but it's stable in nonpolar solvents like toluene. But you can isolate it, and it is also a single molecule magnet. Another ligand we've looked into was phenazine. So phenazine looks like this. This is incredibly reactive. Actually, from everything I just showed you so far, this was the most reactive, possibly to weaker interactions, 2 of these carbons. And so this one nitrogen lanthanide interaction is not so stable. That's one explanation. But it is a great bridge. So even for the non-Kramer-Zine terbium, we're able to see hysteresis. Synthetically, a lot of extra things can happen. If you start heating up the reaction for 12 hours, for instance, then you can induce a CH activation, which is really cool. It has never been observed before for this ligand. So you're sort of getting rid of these hydrogens. And this ligand has not been discovered before, so we're exploring now electrochemistry on this bridge in particular. Also, solvent effect is at play in these sets of compounds as well. If we expose anything to a polar solvent like THF, it actually decomposes the radical right away and induces some other mechanism that then leads to a bridge that is now a dianion between them. And this is not oxidizable to the radicals. We've tried several routes here. Okay, so essentially, this is the summary of what I just said. So we are looking at the same components, same stoichiometry, but different conditions, and then we can successfully isolate 3 different compounds and also purify them. But the best single molecule magnets among these are the radical bridge ones again. Okay, so that's all confirming the theory of implementing strong exchange coupling. Okay. And then we moved to another very interesting system. This is azophenine. It's a little bigger, the ligand, but this is interesting because this has been also employed as a radical between iron centers, so transition metals. And even with the transition metal, which is much less anisotropic, we're able to get a nice single molecule magnet behavior, and in fact, the strongest coupling ever observed in a molecular system. So we thought if we combine this ligand, in particular with the highly anisotropic lanthanides, we should be able to see a much better effect, and this is what we're working on currently, and we're can happily report that we can actually isolate them, but the synthetic route is very different. As you can see, we're doing first salt elimination reaction and then do a reduction. We have to isolate both compounds first, otherwise it's not working. Okay, now so these were all organic ligands. Now I'm going to highlight an inorganic ligand. And why am I doing this? Well, the idea is, we went basically to a bigger ligand, let's go to a very small one. And one very good ligand could be N2, right? Molecular dimension you could pick up from the atmosphere or like really implement it in a glove box. And we had to apply some synthetic trick to make this work. So we remove one methyl group here to then do a N2 activation in presence of KC8 in THF, which then really generates this lanthanide dinitrogen complex. This is an N2-2- bridge. It's a diamagnetic bridge. So this is not a single molecule magnet, but you can isolate that and then reduce it with one more equivalent of KC8 in the presence of krypton, which generates the first metallocene compounds of N2-3- radical bridge systems. And then you can dissolve the crystalline material in 2-methyl-THF, and then you can get a second set of N2-3- radical bridged single molecule magnets. And this was really cool because, first of all, you can decrease the coordination number of the metal from 9 to 8. And additionally, you can increase this dihedral angle from 173 to 179 degrees. Why is this important? That will change the coupling strength between these two metals. And you will see this in a moment. And another thing I should note, if you go to a slightly larger lanthanide gadolinium, actually the 2-methyl-THF does coordinate. So this works for the smaller lanthanides. You can see that a little bit of ionic size radius difference makes a huge difference in the outcome of the products. Okay. So, and you can see here, we have probed temperature dependence of the product of magnetic susceptibility and temperature for all three compounds, and they all show a rising KT upon lowering temperature, which is suggestive of a high angular momentum ground state as a result of strong antiferromagnetic lanthanide radical coupling. And fitting here, so one thing that is really cool about gadolinium is gadolinium has a half-filled F-valence shell. So that means we can use this to basically treat it like a transition metal because its orbital singlet is not complicated by the effects of spin-orbit coupling. Okay, so we can use a spin-only Hamiltonian like you would use for a transition metal system. And when you do this, then you get a very large exchange coupling constant of -20 wave numbers. That's very, very large for gadolinium. And because this is so large, all these compounds are actually really nice single molecule magnets. Okay, and at the very lowest temperatures, you can see this plummeting of KT. That suggests magnetic blocking. And to see whether the magnetic blocking arises from single molecule magnet behavior, we did AC susceptibility measurements. So in case you're not familiar with this, so AC susceptibility is a typical method for characterizing single molecule magnet behavior, in which a very small oscillating field is applied to the sample and the sample response is measured. A frequency-dependent lag between the instrument signal and the sample response indicates whether there is a barrier to rotation of the spin. And if there is, then we observe a nice out-of-phase signals. We can repeat this experiment in different temperatures and then employ a Debye model to extract the relaxation times, and that we can use to construct this Arrhenius Plot. And from the slope of these relaxation times, we can find out the spin reversal barrier. And so we've done this for all compounds, and for the dysprosium 1 and terbium are the THF coordinate versions. These are all single molecule magnets. If you remove the THF molecules, the relaxation times change quite a bit. And that is actually an indication that when you remove THF, you actually make it more axial, the system. And indeed, that's also true for the terbium system. So now we can see the relaxation times from 24.5 to 60 Kelvin. So that was, among this series of compounds, the best SMM. And because we're really interested in looking at all relaxation times from 2 to 60 Kelvin. We're also interested in figuring this out below 24 Kelvin, which is not possible with a squid magnetometer, but with AC susceptibility techniques. But what you can do is you can do DC relaxation experiments if it's slowly enough relaxing. And indeed, we've done this. So in this technique, a very high field is applied to the sample, and then the sample response is measured. Can I ask you please not to speak? It's really disturbing. Anyway, you apply a strong field, and then you watch the relaxation, and if it is an exponential dependence, then we can just fit it easily. And you can see, like, for any normal relaxation, it will be exponential dependence, and so you can extract also the relaxation times out of these experiments. And all these relaxation times can be then used to construct this Arrhenius plot. You can see here, the blue circles are from DC relaxation experiments. The red circles are from AC susceptibility measurements. The relaxation times are as long as 12.6 hours at the lowest temperatures, and at the very highest temperatures, they deviate from linearity. So for a good fit, I needed to use a quantum tunneling term and 2 Orbach processes. And if you do that, then you get 2 spin reversal barriers. One is 276, the other is 564 wave numbers. Already the first one is the largest for a radical bridge single molecule magnet, and that's also consistent with a record blocking temperature of 20 Kelvin for a multinuclear single molecule magnet. And so I think the improvement in magnetic behavior is due to both the reduction of a transverse anisotropy, but also the increase of planarity in the LN2 and 2 plane. Both factors should increase not only the axiality of the ground state, but also that of the excited states. So, and that could possibly enable the relaxation to occur through the excited state. And with that in mind, one point of note is here that this barrier height is actually about double that barrier height. So this result may constitute the first evidence for magnetic relaxation through a spin ladder for any radical containing single molecule magnets, where the energy of this each rung is then determined by a multiple of 2J. Okay, so ultimately, the most important part here is that we'll look at the hysteresis temperatures. So for the THF coordinated dysprosium complex, we have a almost closed hysteresis. And when you remove these THFs, you really open up the hysteresis. So you see that makes a huge difference. And for terbium, already for the THF coordinated complex, we have a very large coercivity of about 3.8 Tesla, and these are open up to 15 Kelvin. But when you remove these THFs, you get to even much larger hysteresis. Okay, so it's here now open to 24 Kelvin. In fact, when you really zoom in, this is a very large range. They're open still up to 30 Kelvin, where the coercivity is 200 Ørsted. So this is the largest coercive field observed for any molecule or coordination solid. Okay, so this was exciting. And one other thing to notice, if we just compare it to what you get out there, what you can buy as a magnet, then it's probably a neodymium iron boron type of magnet. If you compare the hysteresis loops, you can see that the terbium single molecule magnet would outperform the neodymium iron boron magnet in terms of coercivity and remnants. So that shows how exciting the implementation of this type of single molecule magnets were. So our current work is centered of improving this type of research more. So how can we get to even higher blocking temperatures? And so this is sort of an overview slide of the many different areas of magnetism research we're currently working on. I just showed you this bimetallic system. We would like to implement these N2 bridges to make larger clusters, or we would like to make chains and like 2D sheets. And so these are my grad students and postdocs that are working particularly on these projects. I have other students who work on other projects, but this is what we're doing currently. And one very recent result I'd like to quickly highlight is we thought a lot about N2 bridges and how can we actually make that better. And one very neat way would be to really coordinate here a substituent, right? But that isn't easily doable for the interpreter. So this directed our research to exploration of azopyridine type of ligands because they're highly customizable. You can add a lot of substituents, and they have a low-lying azo-centered pi star molecular orbital. So the radical should be achievable, but that has never been observed with a lanthanide or yttrium or any rare earth metal, so we have just came out 2 days ago. So we worked a lot on figuring out how to really generate and stabilize an azopyridine radical in the realm of a rare earth element. And this has worked beautifully. So this is a mononuclear complex. It's a very rare coordination mode where we have crystallographic evidence. The EPR signal here, this is the experimental data we did simulate. For that, it was important to additionally do pulse EPR experiments because just from continuous wave EPR experiments, this wasn't easily to simulate. But ultimately, we were able to, and this is the first high-score experiment on an yttrium radical complex. Additionally, we've done a lot of DFT studies, and we could show that the radical is mainly localized on the N2 bridge of the azopyridine ligand, but it has also some contributions of the pyridyl nitrogens. And very exciting is also the fact that we can actually do electrochemistry on this molecule, and we're able to observe this azopyridine 1- 2- radical state. Okay, so 2 slides quickly. So F-element charge distribution can direct design principles as well. This is the second big approach in the area of single molecule magnetism. What we're doing here is like we're looking at the, again, the charge distributions of each lanthanide ion. And for instance, for neodymium, if we like take all the orbitals and mix them together, then the approximation what we get is sort of a equatorially expanded electron cloud, and this we call oblate. If you do this for the other lanthanides, we get different shapes, but we can sort of categorize them to oblate and prolate. If that's the case, we can basically just, from an electrostatic point of view, we can start matching ligands to these electron clouds. And for these oblate type of ligands, we need sort of an axial ligand field, right? You want to put something up and down, not here because that will squish the electron cloud and then destroy the anisotropy. And so with that idea, we're having a lot of projects there as well. And one of them also just very recently came out where we tried to look into like tetraimidosulfate anions, whether they can stabilize an oblate shape of dysprosium, and that was highlighted on the cover of the Chemistry European Journal. We've done a lot of synthetic work here, so this is mononuclear and bimetallic systems, but I'm not going to go into detail right now. And then we've done a lot of magnetism here, and ultimately in these compounds, this was better, the dinuclear system. Okay, I'm going to skip all this, but I still have a few minutes, right? Okay. So one thing to say is we're also working with actinides, but I'm not going to go into detail why. I will skip this. Instead, I will say that in addition to what I just presented, we're working on metal organic frameworks, mainly on separations and magnetic materials. Then we are developing lanthanide molecular qubits, and you've heard today an excellent talk from Eugenio Coronado, for instance. He has outlined some of the challenges in that talk. We also started doing machine learning to solve some chemistry problems with that. We also expanded our chemistry to main group elements, and we're building an organometallic neptunium lab. That is the first one in Michigan State, and also there are only like a handful of them known worldwide. So this is it will be cool once it's done. These are some of our lab spaces, some of my students. I don't have a recent group picture, but some of my students are here. This is Michigan. This is Lansing, where Michigan State is. This is a picture from the campus. 5 months of the year, it looks like this. And then we have 1 week of fall, which is currently really like this. And then it's just hot. Okay, well, this is my last slide. I'm going to say this here because I know some people will look at this through Zoom too. So I'm the main recruiter for the chemistry department of Michigan State. With recruit, I mean, I am in the recruitment team for students. And I'd like to say a couple things here. So first of all, if you are interested in a PhD program, just apply. There's no application fee. Everything is online. You can Google this. Then additionally, this is also tweeted. These are my inorganic chemistry colleagues. So as you can see, we are 8 professors here at Michigan State. We will give webinars where you can just check out what we have to say, and you can ask questions. It's very informal, but you can ask these questions. These are the dates. Here's registration. Doesn't cost anything. It's just so you get the link on your email account. And so yeah, please apply if you're interested, and we'll see where we go from there. Thank you very much.
Okay, thank you very much, Ellie. We have 5 minutes for questions. One question there.
Sure.
Thank you very much for the great talk. As an experimentalist, I'd like to ask what kind of experimental methods that you are using for collecting this data?
Yeah, so
or is that model dependent?
Yeah, so I'm using squid magnetometry. All right, so squid, of course, for all the magnetic measurements, but also PPMS. Then all these, let me quickly go back to here. All this is basically crystal structures, so X-ray, single crystal, crystallography, but also powder XRD, in case we don't have single crystals. Then NMR, like spectroscopy, NMR, IR, UV-Vis, but also EPR for anything that has open shell ligands, radicals. EPR, pulse EPR, we do DFT. Yeah, I think everything really on atomic level. Elemental analysis for purification. If you're interested in collaborations, contact me, by the way. Not yet, but maybe one day. Not yet, yeah. I don't have one. I think the physics department has one, but I don't possess one.
Some other question? Do you think, I have one question.
Yeah, sure.
Do you think that these D-lanthanides molecules can be used as good materials for quantum computing or not?
Yes. Yes, and it is. So I have not talked today about qubits.
And
but
how you can increase the interaction between one molecule and the other?
I mean, everything I talked about today was molecular magnets. Our qubit research, really, that is, I mean, the qubits are really for quantum computation. In that particular case, what we do is we're implementing ligands that are nuclear spin free, so you have only one active site. And then we use a lot nuclear spin free solvents like carbon disulfide. It's just important that you don't have any spins around the qubit. So this is what we're doing currently.
I don't know if there are questions on the chat, because it was impossible for me to follow. No questions on the chat. Any other questions in the audience? Miguel, do you have questions? Sure.
Well, for the EPR measurement that you said, the simulation,
Yes.
do you use your own simulation with a model, or do you use some kind of software?
No, we did not use a software. We
Okay.
calculated everything. But just so, that's a good question. I'm going to go quickly back because I think, so let me explain it. So when you get a signal like this, here, this is just, I mean, it's super exciting, but it's also a nightmare if you think about how am I going to simulate this? Has so many hyperfine couplings. It's probably a combination of nitrogen, hydrogen, and yttrium cores. And that is arising, so it's not symmetric, right? It's not symmetric because the coordination environment is not symmetric. So you have a very unusual coordination here. So that means we had to do, so this is a continuous wave EPR spectrum. But when you do high score spectrum, this is a pulse EPR technique, then you can figure out the spin contributions of the nitrogen ligands. And by doing this, so this is the experiment, this is the simulation. We simulated this based on the experiment. And from the values we get here, we were able to simulate this. This is the simulation. So that is first high score. It just came out 2 days, so read it.
Okay. Other questions? If not, thank you very much again, Selvi.
Okay, thank you. Thank you very much.
Thank you.